expectation is the mean. Expected value is the mean. Right. Having this in mind, now there is an example here. Suppose x is a discrete random variable with probability mass function. If you remember what is probability mass function is the probability value set you assign for each of the random variable. So you have, if x is equal to 0, you have a probability of 0.25. If x is equal to 1, you have a probability of 0.05. If x is equal to 2, you have a probability of 0.25. And you add them together, 0.25, 0.25, 0.5, 0.5 plus 0.5, that is 1. So the probability space is contained. The summation is 1. So the expectation is simply x fx sigma from starting from 0 to 2, because you have three random variables starting from 0, 1, 2. You simply calculate 0 times 0.25 plus 1 times 0.5 plus 0.25 times 2, and you get the answer 1. That is the expectation of it. Okay. So if you tweak this a bit, if you change the value you assign for this random variable, maybe instead of 0, you give some other value. Instead of 1, you give some other value. If that is the case, the expectation is going to change, right? The probability, of course, is an inherent property in that distribution. Probability you can't change, but you can change the value assigned for x. Right, since we don't deal with continuous variables at this moment, let's move forward. And you can actually take it from just the random variables to functions as well. We'll talk about functions if we encounter any in the future. So the simple idea is this. Now, if you have a probability mass function, the same probability mass function, and if you calculate the expectation of x square, remember, for the same probability distribution, the expectation of x was 1. But now we are going to calculate the expectation of x square. The expectation of x square from the definition is simply the summation of x equals 0 to 2 x square fx. Right? So the x square comes from whatever you put inside this expectation symbol, which is whatever you put inside this e inside bracket here, this becomes the multiplication value inside the function. So sigma, whatever that you put, fx. Okay. I hope that's clear. Whatever you put inside the expectation, E inside bracket, that becomes the multiplying factor of this sigma xfx thing. So here, because it's E x square, it becomes x square fx. So when we do the math, x square fx, 0 square times the probability 0.25 and so on and so forth. You calculate as you calculate this square value, 1 square plus 2 square and so on and so forth. Now the expectation get a different value. The expectation of x square. Expectation of x square 1.5. Expectation of x is 1. Now, by the look of it, you can easily see that expectation of x is not equal to the expectation of x square. Right? That's a numerical example. And also, this gives us a very interesting phenomena. If you take expectation of x, that was 1 for this one, and expectation of x square, which is 1.5 for the same example, if you take expectation of x and square it, then that is equal to 1 square, which is equal to 1. And that's also not equal to the expectation of x square. These are not the same. So expectation of x square is not the square of expectation. Remember that very clearly. The expectation is, let me go back to the initial discussion. Expectation is simply the mean of it, of the distribution or the value set. But expectation of x square is not equal to the expectation of x. And also, expectation of x square is not equal to the square of expectation. So all these things need to be remembered clearly when we move to the next one. So the next one is called variance. So now from your school days, you might have learned about this variance and standard deviation. But the definition of variance is, it is the expectation of this. I repeat, it is the expectation of x minus ex square. Okay, take this idea very clearly. Variance of x is equal to the expectation of this thing. Right? So by definition, remember, expectation of something is equal to sigma of that thing fx, f something, this thing. Right? So by definition, expectation of this is equal to sigma x minus ex square f of x minus ex. So that's how the definition works. So simply this becomes x minus fx. That's the same probability because the distribution is the same for the x. And the calculation changes to this. When you want to calculate the variance, what you simply do is you calculate the x bar, that is the mean of the distribution, and minus this from every observation in the distribution. So for example, if we go back to our initial example, which is this one, right? If I go back to the initial example, so this is my initial example. Now, if you take the same example, what we do is we take xi. Xi is going to be 1, 8, 12, 15, and 22. And first of all, you need to calculate x bar. X bar is the mean. So the mean was, I forgot what is the mean. So it was somewhere around 11.6, right? And then you calculate xi minus x bar first. So 1 minus 11.6, 8 minus 11.6, 12 minus 11.6, 15 minus 11.6, 22 minus 11.6, right? And then you calculate the square of this. right? And then calculate the mean of this expectation of x minus x bar. That is the variance. Ex minus ex square. So that's the variance. And I will talk about how this expression comes now. The expectation of x minus ex square, we need to simplify this expression. So I'm going to simplify this expression. X minus ex square becomes expectation of x square minus 2 times x expectation of x plus expectation of x square. And that is going to be now expectation of x square minus 2x ex. From the properties of this expectation, you remember expectation of ax plus b is equal to the a times expectation of x plus b, right? Using this property, we will take the expression and expand this. So expectation of this is equal to expectation of x square minus expectation of 2x ex plus the expectation of x square, rather square of the expectation. All right, so this is what we get. Now we get something interesting. Expectation of x square minus 2 times, right, 2x, 2, let's put it 2 times x expectation of x plus expectation of square, right? So because of this thing, this particular thing, you take the let's say yeah, so because expectation of a constant here, you go to the definition here, expectation of a constant is the constant. So we have expectation of x square minus 2 times expectation of x plus expectation of square x square. And what do we get here? This is 2 times, right? So this is ex is a constant because ex is a value, right? Then we have ex inside minus 2 times ex, that is going to be ex square plus ex square. So 2 times ex square plus ex square is going to be minus ex square here. So that is the expression that you find here, right? So in the exam, you might get, like, for example, because you can get different formulations, you might get ex in one sense, you might get ex square in one sense, and ask to find what is the variance of x. Then you just simply get the answer. All right. So again, if ex square was equal to ex square, if this happens, the variance is going to be 0, right? If ex square is equal to ex square, the variance is going to be 0. Think about a scenario in which this can happen, where the x square probability values will be equal to the or the mean of the square values will be equal to the square of the mean. And that's an interesting thing. Think about it. There can be instances, if you think, right, ex square minus ex square. Oh, that may never happen. Think about it, because those are good things to think about, right? And the standard deviation of a random variable is defined as the standard of x, that's the square root of the variance. So if you have ex and ex square, you can calculate the standard deviation as well as the variance, right? So there are some properties about variance. Now remember, about the expectation, if it was ax plus b, that is equal to the a times the expectation of x plus b, right? For the variance, that's a bit different. Variance ax plus b is equal to the a square of variance x, right? So think about how that can be derived. I'll give you a little bit of a hint. Variance of ax plus b is equal to the expectation of x square minus the expectation of x square. So you put the expectation of x square, that is ax plus b square, minus the expectation of ax plus b square, right? So in other words, if you expand this inside the expectation, that is going to be a square x square plus 2abx plus b square minus, now by definition, eax plus b can be written as aex plus b, right? Remember, it was given right up here. So by using that property, now I'm going to expand this again. Expectation of a square x square plus 2ab expectation of x plus e b square minus, and I'm going to expand this. So that's a square sign, and I'm going to expand it a square ex square plus 2ab ex plus b square, right? Forget about these parts. I'm just focusing on the expansion. So that's going to be e to the power a square x square plus 2ab ex plus eb square minus this. We have a square ex square minus 2ab ex minus b square. So this is going to cancel. And remember, E of C is equal to C. So from the same logic, E of B square is going to be B square. So E of B square is going to be B square. Because of that, plus B square is going to cancel out with minus B square. And we have A square E of X square, right? That's here. And minus A square E of X square. And what will happen now? We can take A square out, and outside, then we have inside EX square minus EX square, which is the variance of X, right? So that is how the variance of AX plus B is equal to A square variance of X, right? So now I have explained how it happens, and don't tell me that in the exam I haven't done that. So if you have any variable of, let's say, if you have a random variable, and the questions can be formed in different ways. For example, I can give you a random variable and ask it to be stretched by some value, say 5 times of x plus, let's say we can change the reward mechanism. There is a reward mechanism where if you get a random variable, you get 5 times of that plus something, then what will be the variance of it? So and this is the way to calculate it. Like if it is variance ax plus b, that is going to be equal to a square of the variance times x, variance x. So you have other questions here. And that concludes the first part of the lecture. Let's move to the next one, which is about probability distributions. Let me take another page and right. Okay. So the discussion would be primarily on probability distributions. So what do you mean by a distribution? Now take a piece of paper and organize your thoughts. What sort of distributions are we going to learn here? Right? So let me write the things for you. I'll start my distributions here. So the first one is a discrete uniform distribution. Write this down on a piece of paper. Discrete uniform. Then Bernoulli distribution. Bernoulli distribution. And we have geometric distribution. Negative binomial, geometric, negative binomial, hypergeometric. Geometric, negative binomial, hypergeometrics. Right? I will just write it down here. Negative binomial, hypergeometric. I think I missed the third one. That is geometric. Hypergeometric. For the time being, let's keep it like that and let's move on. Now, why have I asked you to do this? To write down the distribution is for every distribution, you will find the expectation and the variance of that particular distribution. So what is a distribution? Now I cannot get an answer from you, right? I cannot ask a question from you because I cannot hear what you say. Now think about this. Random variable x is said to have a discrete uniform distribution if each of the n values in its range has equal probability. So what does it mean? Now take a piece of paper and think about this. The same example that I have given you earlier, where you have this, remember? This was our initial example, earlier example. So we have a set of values 1, 8, 12, 15, and 22. Now this is a discrete uniform distribution because each of its values. Now I have x1. What is my x1? My x1 is this. This is my x2. This is my x3. This is my x4. And this is my x5. I have 5 elements and I have 5 values here. For each of them, you have an equal probability. So what is that equal probability? That is equal to the number of values I have. 1, 2, 3, 4, 5. 5 values right here. And the probability fx is equal to 1 over 5. So now this is a discrete uniform distribution. So simply what this means, it means that if you draw them where you have the x value on x scale and the probability on your y scale, so let's say fx, then you get a constant probability of 1 over 5 for each of these values. Now the things that we deal with are basically discrete values, so you cannot draw a line. It's just a simple 1, 2, 3, 4, 5. This is the probability mass function. Forgot, I should not put them in the same sequence because I have 1, 8, 12, 15. They are not the same. So assume that they are the same. Forget about the distances. So 1, 8, 12, 15, 22. All of them have equal height of probability 1 over 5. So basically, in the case of uniform distribution, you are dealing with same probability for each outcome. And that outcome probability is equal to 1 over n, where n is the number of values in its range. Okay. So dissolve this idea because that's important. Now, if you took a value, any value out of it, the expectation of x is equal to a plus b divided by 2, where a is the starting value, b is the ending value. Okay. So let's look at this one. A plus b, that is 1 plus 22 divided by 2, 23 divided by 2, that is 1.5. So let's look at our example earlier. What is our expectation? I think it was somewhere here. Was 11.6. Yeah, was 58. So somewhere that. All right. Now in this case, the expectation is given a plus. Now this is when we talk about a very long range, very large value, then 11.5. This is let's check whether 9, 21, 36, 58. 58 divided by 5, that is 116 divided by 10, that's 11.6. Here 1 plus 22 divided by 2, that's 11.5. Not the same, but when it is a uniform distribution, expectation can be calculated as this. And then you have the variance of x, that is here, b minus a plus 1 square, all of it square, minus 1 divided by 12. So take a piece of paper, write your uniform, whatever the distribution, and write the expectation and the variance, right? What is expectation and what is variance? Write it in front of that name. So expectation is a plus b divided by 2, and the variance is, write it down, right? So you do that exercise. Let's look at this. The cast of a fair die is an example of a discrete uniform distribution. That is because when you look at a fair die, the fair die will have 1 over 6 of probability, right? So all those outcomes will have equal probability of occurring, 1 over 6. Right. Now we come to a very important question, Bernoulli distribution. Experiment that has only 2 possible outcomes is called a Bernoulli experiment. So what is an experiment that has only 2 possible outcomes? One particular example is tossing a coin. A coin might have head or tail, right? So 2 possible outcomes. And another example is a yes or no scenario. If you ask someone about whether you know about this, that person can say yes or no. So that's 2 possible outcome experiment that has 2 possible outcomes. It's a Bernoulli experiment. So whenever we talk about a Bernoulli experiment, please keep this in mind that we are only referring to 0, 1, either a yes or no. Yes or no. Right? The yes or no can be anything. If it is 0, yes, 1 should be no. If it is 0, no, 1 should be yes. Anyway, the Bernoulli experiment is something that talks about 2 possible outcomes. 2 possible outcomes, right? So if you want to model something in terms of a Bernoulli distribution, you always have to find what is that 2 possible outcome. What are these 2 possible outcomes in that particular experiment? Also, success and failure is a common way of defining the outcomes. So we can define success as 1 and failure as 0, success as yes and failure as no. It can be anything. It can be a disease, it can be victory, or it can be winning something or not, or it can be going somewhere or not, yes or no, anything. Success or failure. Now, if you go back to our examples about random variables, X can be 1 when outcome is a success, 0 when it is a failure. So throughout this course, let's define success as 1 and failure as 0. Right? So let's agree that when we discuss something in the class and we do a question, we define success to be 1, failure to be 0. I hope you are agreeing to me. And when you are doing the calculations, all the time refer to a 1 as success, to a 0 as a failure. Now, if X has a Bernoulli experiment outcome, X is a Bernoulli experiment outcome, 1 or 0, then X is said to be a Bernoulli random variable. So what constitutes a Bernoulli random variable? You need to have 2 outcomes, success or failure, 0 or 1. Okay. If the probability of a success is P, then the probability mass function is this. The probability can vary from P to 1 minus P depending on the state. If it is a yes, as I said, we'll talk about success as 1 or yes as 1, no as 0. So if it is a yes, the probability is simple P. If it is a no, the probability is 1 minus P. Why? We need to make sure that the summation is equal to 1. So 1 plus 1 minus P, that's equal to 1. The probability space is contained. It's limited and it's greater than 0 within 1, less than or equal to 1. So if that's the case, the expectation is P and the variance is P times 1 minus P. Now I'll give you a very simple example. Tossing a coin, when you toss a coin, right? Let me show you something. Right. I hope I'm visible in terms of the screen. Okay. So if you take a coin, for example, take a coin. Things I have a coin. Yeah. All right. So let's take this coin, right? So the coin, right? This is a tail. Let's say this is the tail and this is the head. Okay. So this is the head where you have that national symbol and this is the number 5. So head or tail. And the expectation is P, which is the probability of the outcome. All right. So if we give x equals 1, that is our head, the symbol, and the probability of getting that is 0.5. So the expectation is 0.5. So that's how actually 0.5 comes, right? And the variance is 0.5 times 0.5, that is 0.25, right? So that's the idea. Expectation is the probability, variance is the probability times the probability of the negative outcome or failure. Okay, let me repeat it again for you. Expectation is the success probability. Variance is the success probability times failure probability. Okay. So I hope that's clear. Now, let's go down a bit. We have a binomial distribution. Okay. So binomial distribution is, yeah, Bernoulli distribution is a distribution of Bernoulli random variable. Binomial distribution is a sequence of n repeated Bernoulli trials. So what is the difference here? A Bernoulli distribution is when you have a success or failure, right? And binomial distribution is an n repeated Bernoulli trials such that the trials are independent. So tossing up a coin, right? Imagine you are tossing a coin. So n repeated Bernoulli trials have a head, tail, head, tail, 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 head, head, tail, tail, head, 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 tail, 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 head, tail, something. That's an n repeated Bernoulli trial. Each of these outcome was a result of a Bernoulli experiment, right? N repeated Bernoulli trials. The probability of success for each trial remains constant. That's important. So when I toss this coin, the success probability was P. When I toss this coin, the success probability was P. When I toss this coin, success probability is P, so and so. It doesn't change. The coin doesn't change. So if the coin changes, you cannot tell it's a binomial distribution. Okay. So let X denote the number of successes in the n independent Bernoulli trials, which means let's define success as uh, as obtaining head, right? Number of successes, so that is X. Now we need to check, right? Number of successes. Let's look at number of successes. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 successes. Number of successes in the variant. Then X is said to have a binomial. So how many failures are there? Let's check how many failures. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 failures, 8 successes. X denote the number of successes in the n independent Bernoulli trials. Then X is said to have a binomial distribution. So it has a binomial distribution with parameters n and p. So p doesn't change. P remains constant. That is the probability, which is in the coin example, p is equal to 0.5. P doesn't change. N is what? N is the number of independent Bernoulli trials. So in our case, n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Or in other words, the summation of the successes and failures. 8 plus 12 is 20. Right? So in our case, that is 20. Number of, or the probability is 0.5. That's a coin. So binomial NP, this is how it is written. Binomial NP, its probability mass function is given by probability of occurrence x is equal to ncx px 1 minus p n minus x. So x is this number of successes in our simple example 8, which is true because x plus n minus x should be equal to n. That's a total. X plus n minus x, that's because the total number of items should be equal to the successors plus failures. Right? Right. So the expectation is NP and the variance is NP 1 minus P. That's the binomial distribution. Right. So with that, we'll do this example and finish the lecture today. And we will do the lecture tomorrow from here onwards, from geometric distribution onwards, right, for the Poisson. But let's look at a simple example from binomial distribution. So you have each sample of water. Now let's look at how this is becoming a binomial distribution. Now let me explain it. So each sample of water has 10% chance of containing a particular organic pollutant. So if you take a water sample, you have a 10% chance that this water sample will contain a particular organic pollutant, so whatever pollutant. Assume that the samples are independent with regard to the presence of the pollutant, which means they are independent. If you take a sample and another sample, the second sample does not depend on the first sample. That's what it says. Find the probability that in the next 18 samples, which means you start from somewhere, 1, 2, 3, 4, all the way, 18 samples, exactly to contain the pollutant. Right. Find the probability that at least 4 samples contain the pollutant. Okay. So you can see the questions. Now I'll give you 5 minutes to attempt it. Now it is 2:20. I'll give you 5 minutes to attempt it, and then I will explain how this is done. Right. So let's look at this question. All right. Let me explain to you what happens here. Now the question, let me check a different color. maybe purple, right? Now, let's look at the question from a broader angle. You have 18 samples, right? So for the simplicity, let me take, okay, let's, for all practical purposes, let's look at this from a very simple angle. Now, I'm going to get this shape, right, to represent right. Let me check. Yeah, this will represent a sample. Okay. So I have 18 samples. So I have 1, 2, 3 now. And that is 6. Then I have, okay, I have 12 samples and 18 samples, right? So I have 18 samples now. And I'm going to I'm going to color them as, okay. So this is, so I have 18 samples. Let me put like contaminated. Oh, okay. I'm going to color them from this color. This is purple. If the sample was okay, that is no contamination, I will color them using purple. So these 3 were contaminated, or they have a, say, contaminated, let's say, false, right? Oh, sorry. We are asked to find if there are only 2, right? Exactly 2 contain the pollutant, right? So this is what I have, all right? 18 samples, 1, 2, 3, 4, 5, 6, 6 times 3, 18 samples, and 2 contain the pollutant, right? Now, if I write this as a string, listen to me very carefully now, okay? If I were to write this as a string of values, I can write S, 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 F, S, S, right? And then the next round, S, S, F, S, S. The last one, S, 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 right? So that is my success and failure. There are 18 values. Now this F and this F, right? These are the failures. So in other case, all right. Sorry. So when you have exactly 2 contain the pollutant, right? Those are our successes, which is like the definition has to be changed a bit. I'll change it. Instead of F, I will write S here because success is having a pollutant. Okay. Success is having a pollutant because we are looking for the pollutant number. If it is other way around, you can define it as a failure. But here we are asked to calculate to contain the pollutant. So having the pollutant is a success. So in other words, you have F, and this is an S, and then you have FF, then you have FF, S, F, F, F. The last part, F, 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 F. 1, 2, 3, 4, 5, 6. Right. So these are the successes where you find the pollutant. Now look at the example. It doesn't say where you find this pollutant or where you find this 2 contain the pollutant. It can be here, or this S can be somewhere here, somewhere there. So just 2. So you have 2 S's and 16 F's, right? So it's a matter of organization. How many ways can you organize this? In how many ways can you organize this? All right, that is 18 C2. You take 2 out of it, and you have 16 F's, 2 S's, and you are going to pick 2 out of this. And if you do that, you will find 18C2, right? So that is why the probability equation has this NCR. The remaining part is very simple because the probability of success is Px and 1 minus P n minus x. So n is 18. You have 18 total number of letters. 18 minus 2, that's what you are looking for, P of 2. So probability of finding pollutant, so that's 0.1. 0.1 into the power 2. 1 minus 0.1 into the power 18 minus 2. This is the probability because you only have 2 S's and 16 F's. So that's the probability. That's very simple. But you can have multiple ways in selection. So 2 of this would be selected. That's why 18C2 comes. Right? Now I hope you understand it. So each sample of water has 10% chance of containing a particular organic pollutant. So 18C2 to pick 2 out of it, and then this can change. So basically what it says is, if you organize if you pick 2, that 2 can come from any of the point here. So that's what it says. The 18C2 simply means the number of possible 2's out of this 18 that you can get, and then you find the probability, because this doesn't change. This is just the way it was organized here, but in somewhere else, this S will be somewhere here or there. Doesn't matter, but you can have multiple 18C2. So the ways in which you can order 2 would be 18C2. Right. So think about it. Right. The other way of looking at understanding this is actually coming from your binomial expansion. If you expand the binomial expansion, a plus b square, that is equal to a square plus 2ab plus b square, right? If it was a plus b to the power 3, that is a cube plus 3a square b plus 3b square plus b cube, right? These fractions, coefficients, basically indicate what we call a Pascal triangle. And these values indicate how many times they are repeated, these combinations. That is how this coefficient 18C2 also comes. So you can look at it from that angle as well, because the total number of items that you can have, 1 plus 1 minus p, and put to the power n. That's how this thing happens, because it's a binomial trial. So it keeps on repeating. Because of that, number of binomial trials are there, and then at the end of the day, this is the expression that gives us that final abstract idea of
number 2 outcomes. So the question number B, find the probability that at least 4 samples contain pollutant. So it's straightforward. If it is 4 at least, you take equal or greater than 4. Also, you can take less than 4, 1 minus that. That will give you the same answer. Each sample of water has 10% chance of containing a particular organism. We assume that the sample are independent with regard to the presence of the pollutant. What are the mean and standard deviation of X? Now, this is an interesting question. What are the mean and standard deviation of X? The number of samples that contain the pollutant in the next 18 samples analyzed. E of X is NP, Y of X is NP times 1 minus P. So you have to remember this. In the exam, I'm going to ask you these questions. You have to remember this. Expectation of a binomial distribution, that is NP, variance NP times 1 minus P. So it's basically N times P1 minus P. So if you remember the Bernoulli trial, if it is a Bernoulli experiment, expectation was P, variance is P times 1 minus P. Now, in the case of here, in the case of repeated Bernoulli experiments, which is a binomial distribution, you simply have expectation as NP and the variance as N times P times 1 minus P, which is simply an addition of N because it's a repeated Bernoulli trial. That's the difference. So you can easily remember what it is. Okay. So I will stop here for the geometric distribution and hypergeometric distribution. I will do this tomorrow. And with that, I think we can complete the lecture series for the probability, and then we can start the statistics lectures. And I think, yeah, we'll stop it here. I will share the recording on the Moodle and you can refer to it. Okay. Okay, thank you. I'm going to stop here.